Okay, so we're starting with collisions. The main thing we're going to be doing here to start off is looking at Newton's laws and how they apply to collisions. And we'll see that one of the most important formula comes out of it. So, first of all, this is an example of a collision. We've got a truck and a small truck, they collide together. Something happens afterwards, we're not interested right now. Second example, a ball hitting off a wall. So the dark black ball there is going towards the left with speed u initial, ui, hits off the wall and then rebounds back, and the dotted ball is the rebounding back object. And the third one, a tennis ball or a snooker ball or something like that hitting off a wall and rebounding back at an angle. And Newton's laws need to apply here. So the first one is this. In each case, as a result of the collision, the particles change their velocity. And if they change their velocity, it means they accelerate. And if they accelerate, there must be a force acting on them. So in the case of the two lorries, when they collide, let's say it was a bizarre scenario where they just collided off each other and went back in their opposite directions. So the blue truck is going to the right, hits off the small one and goes back to the left hand afterwards. The only way it's going to change its direction is if it receives a force to the left. By the same token, then the smaller truck will receive a force to the right, and that will go to the right. The same thing happens with the second situation and with the third situation. In other words, there must be a force causing the velocities of the objects to change during the collision. Now, what's really important to remember then is both objects will experience the same size of force but in opposite directions. And I inferred that when I talked about the top diagram. The blue truck will experience a force to the left during the collision. The small truck experiences a force to the right during the collision. With the other two systems, the one in the middle, when the ball hits off the wall, when it's going from right to left, it hits off the wall, it will experience a force to the right, which causes it to change direction and go to the right. But according to the sentence there in the bottom left-hand corner, which is Newton's third law, the wall will experience an equal and opposite force. And then the bottom section, the ball hits off the backboard. As a result, it experiences a force. In this case, the force will be perpendicular to the plane. Actually, it's always perpendicular to the plane. The force will be experienced by the ball. That causes it to change its direction in the J direction in that case. And the backboard experiences an equal and opposite force. So what about the size of the force then? Well, Newton's second law is F is proportional to mv minus mu over t. And then if we use SI units, we can convert the proportionality to an equal to sign because the constant of proportionality is a 1. So the force is equal to mv minus mu over t. The m's are the masses of the mass of the object. So for example, it's the mass of the blue truck. That would be the m you'd fill into both of those values. The u value is the initial velocity of the blue truck going into the collision. The v value is the velocity of the truck coming out of the collision. The f is the force that it experiences to the left. And the t then is quite interesting. It's the time over which the collision is being experienced. And that's quite interesting because of the following. If you cross multiply, you get f by t is equal to this thing, mv minus mu. Again, m is the mass, and u and v are the initial and final velocities of the single object. The force is the force experienced by the object, and t is how long that force is being enacted upon the object. The reason it's interesting is because in sports like tennis, the strings in the tennis racket are flexible, and what that does is it makes the tennis ball and the racket remain in contact with each other for longer than would be normal if, we'll say, the strings were made of a hard material or they're made of wood or something like that. So then how that applies to the equation is the t value is large, the f value is large, so that means the thing on the left is actually quite large as a result. Now if we were to compare that with something like, let's say, cricket, you've got a solid bat and a solid ball, so when the ball hits off the bat, it rebounds much, much quicker than in the situation with the tennis ball and tennis racket. So t is smaller for cricket. As a result, the t by f would be smaller for cricket, and therefore the mv minus mu would be a smaller quantity as well. In other words, the change in velocity would be less for cricket than it would with tennis. And we used to play rounders as kids, and we'd alternate the balls that we used. So when we used tennis balls, we found that the ball would go much, much further. When we used harder cricket balls and stuff like that, the ball wouldn't go as far. And the reason comes down to the tennis ball would squish when it comes in contact with the bat. If it squished, it was in contact with the bat for longer. That T value was larger on the left-hand side, which meant that the right-hand side was larger then as well. So any change in velocity was larger as a result of that T value being bigger. It also comes into play when you jump or when you land. So when you land after jumping from a height, you're supposed to bend your knees, like is illustrated in the image. And what that does is you cushion the blow of you landing. And when you cushion the blow, you increase the time that the force of you landing is enacting over your body. That F by T has to be a particular value for you to ensure that you come to rest within a certain time frame. And as a result, if that T is large, that F can be a bit smaller. Also, when you're catching a ball, what this guy will generally do if the ball is coming towards him quickly is he'll have his arms outstretched, and as the ball hits his hand, he will bring his arms towards him with the ball. So to explain that again, if we look at our formula, you have an mv minus mu. The ball is of mass m, it's got a particular velocity v, and you want it to come to rest, so you want the u value to be 0. So there's a certain value there on the right hand side. To get the same size value on the left hand side, you either need to exert a large force on it over a small time, that will stop the ball, or what you do is you exert a small force over a longer time, and then when the ball comes to him, he doesn't have to exert that much of a force on the ball to make it come to rest. And the fourth place you'd see this is with cars. So in front of the car there's the bonnet, and sometimes in front of the bonnet there's some empty space. It's called the crumple zone. And if a car is going at a certain velocity and hits an object and comes to rest, the right hand side of that equation, mv minus mu, will have a certain value. So in order for you to come to rest in the car, one of two things have to happen. Either you have to exert a large force on the car over a short time, in which case it'll be quite dangerous for you in the car, or if you stretch out the time through which the two objects are in contact by having that crumple zone crumple during the collision, you will need less of a force experienced on the car, and that will have less of a damaging effect on you. Okay, that thing on the left hand side, it's got a different name as well. If I take out ft, ft is often given the symbol I, it's called the impulse. So the impulse there is a vector quantity, and for the fifth years you need to fill in the vectors in ij form. So what I mean by that is, instead of the v and the u, you'll need the vectors in I and j form. You'll fill those into the equation, multiply them by the scalar m in each case, and that will give you the impulse in vector form. The other thing that I'd note is the impulse is always perpendicular to the plane. So in the case of the tennis racket, it's perpendicular to the flat section of the tennis racket. In the case of you jumping off an object, it's perpendicular to the floor, so straight up. And in case of somebody catching the ball, it's perpendicular to the surface that the ball hits. That's extremely important. Extremely important. Okay, so a few more examples. In this case, you have a ball there going to the left. It's got a speed of u, so its velocity there will be minus ui. And then afterwards, it's traveling to the right, so its v value afterwards is plus uf as well. And to calculate the moment, you'd fill in the I and j component and multiply by the mass. Now the impulse then, when the ball hits the wall, the impulse the ball experiences will be to the right. Second example. So the ball comes out at an angle, hits the wall. The impulse in this case is perpendicular to the plane, so the impulse will be in the downwards direction, or the j direction there. What you'll need to do is get the velocity of the ball in the I and the j direction beforehand and afterwards, fill those into the equation with the mass, and what you'll find is the impulse is indeed got a negative j value. It's downwards in other words. And then in that case, it'd be the same thing, lads. V and U, you'd fill those in IJ form, and you'd work out the impulse. And in that case, then you'd see the impulse is directed away from the surface that catches the ball or perpendicular to the plane. Okay, let's have a look at a question. A ball arrives at a batsman from a bowler at 30 metres per second. The batsman hits the ball directly back towards the bowler at 20 metres per second. So we have a one-dimensional system. It's just left and right as far as I'm concerned. The mass of the ball is 0.25 kgs. Calculate the impulse imparted to the batsman by the ball. So I'm going to say it's something like that. The blue one there, or sorry, the black one is the velocity before it hits the bat. I'm representing the bat with the rectangle. So in IJ form, the initial velocity will be 30i. It experiences an impulse when it hits the bat, and then afterwards it'll have a velocity of minus 20i. So there are my quantities. M is equal to 25. Take out your formula and sub it in. So 25 by, that should be minus 20i and plus 30j. So my signs are incorrect there. And then when you work it out, as far as I know, that actually is correct. You get minus 1375i, and the units of mass by velocity, kilogram meters per second. So that answer is actually correct for it. The minus tells me that the impulse is experienced to the left, and that's what you'd expect. So when the ball hits the bat, the impulse is trying to hit it in the opposite direction, and it ends up going in the opposite direction. So that would make logical sense. Okay, so I want you to remember this. The impulse is often referred to as just the change in momentum. So we need to define momentum in a moment, and we'll see momentum is just mass by velocity, and we're looking at the change in momentum there. Okay, for you guys, this is the end of the first video. You might do both of those questions.